Hello, hello, hello. Good afternoon, Internet. Welcome. Oh, my goodness. My goodness, my camera's way off. There we go. That's better. Welcome. Welcome back. Welcome back to, what are we on? Day 61. Boy, oh boy. Day 61 of NL Math Man's Math Help Streams. We see today here behind me, I'm getting sniffed by the doggies, apparently. Right? They must have. I guess they probably spotted like some sort of shrew or vole or something like that. They're always every time they're out for a walk. There's always like something. There's something in the grass, and they'll just like go over and zoom right in on it. And be like, oh, this is the most interesting thing in the world now for a solid 30 seconds. And like, it's so hilarious. It's so funny, especially in the snow. Flurry will just go over and just jam her face directly down into the snow. Like she'll just be walking along, and then all of a sudden, I guess, just smell something randomly off to the side, and she'll just trot over, and then boom, face just directly down into the snow. Like kind of like when you throw a ball and it just lands somewhere and it doesn't bounce at all, and it looks kind of funny. But her face is the same thing. Like she just plant, and it just doesn't move and just stays right there. Then like sometimes pulls up and plant again. Right? It's pretty funny. But anyway, so that's sort of what's going on here. Although I'm right in the position there for them to be maybe they're sniffing my COVID cut here. Look at that, right? Yeah, a nice beard trimmer haircut. I'm almost due for another top up here now, right? Like it's getting almost long enough to comb it again, right? So maybe I need to take the beard trimmer back to her again. You know, see if I can get some more artistry out of it. I won't even need to get, well, I guess you can go to hairdressers again now, right? Yeah, you totally can. Um, maybe that's a way I'll save some money though. Continue using my beard trimmer to cut my own hair. Maybe not. Maybe not. I think I can sacrifice the $20 every, I don't know, 6 weeks or whatever. Right? It's okay. Um, yeah. So over here on the side now, I've got a list of topics that I'm going to get to today. Don't have a whole lot of banter to introduce the stream with today. Um, yeah, we are getting down toward the end of it, but I don't exactly have a lot of fanfare right now for it. Normally we would have a bit of fanfare right in the summer. I like to I wait, hold on. Am I getting a bit of I think I'm getting a bit of blueness bleeding through. Hold on a second there, Twitch. Let me change my lighting here in the room touch. Yeah, I think that might be better. Anyway, yeah, we usually have a little bit of fanfare at the end of the school year, especially in the summer. I used to bring out used to, I guess, every other year except for this one. I'd bring out charcoal barbecue or whatever, and we'd have a bit of a cook up sometimes. That was always fun. Occasionally we just have pizzas or maybe a potluck, but usually in the summer it was a charcoal barbecue before we close, which is nice. It's a good way to spend the final day out there, but there won't be anything like that this year. Closest we'll have is maybe a shorter stream on Friday where I don't have so much correct. Well, I will have a lot of correcting to do, but I guess I won't really have a whole ton of topics to talk about. Seeing, it'll be either a solid 2 months before students are back at it again, or they'll be with a different teacher come the following Monday. So me telling them what I want them to write down is not necessarily super relevant. Anyway, yeah, well, I guess we'll deal with that when the time comes on Friday. Hey, but up until then, it's gonna be a lot of correcting in the meantime. Right? Over here on the side, then we've got our. Oh, see, I'm used to motioning the other way. Over here, now we've got our topics for today. Going to go first into a bit on distance and velocity time graphs. We're going to talk about just a few more points for the Physics 1104, which is the intro of the general physics or it's the intro of the physics ones. There is no general physics. It's just the anyway, the introductory physics course. And like I said before, for all these topics, it's sort of a more simple look at what we'll get onto later. And if anything, for my money, the stuff we get onto later is a lot more makes a lot more sense, right? When you actually start incorporating some of the other factors. But we'll see. Excuse me. You see what I mean as you carry on with those. Graphing quadratics will be a very quick bit for Betty Ann's course. I'll just really briefly go over axis of symmetry and vertex and just a few terms, really. Probability and NCR NPR recap, that'll be for Calais. So that'll just be a few questions off an activity you did recently as you're getting ready for your final exam in that course tomorrow, I believe. And then sine and cosine laws review, that'll be for Bev. I know Bev's not able to watch the streams. She might be able to watch afterwards, or at very least she'll get the notes that I'm sending out. So I'm going to leave that one until last because I know she won't be watching live. Anyway, yes, so then without further ado for today, I will get into the physics section, the distance and velocity time graphs. Oh, I am way off indeed. Okay, let me zoom in. I even need to sort of square it up a bit too, because it's sort of on a slant. Right? We're not looking at an isometric sort of overhead view here. I want a straight on. I want a top down, nice two-dimensional view. Right? Although, you know, right, nothing is two-dimensional, but we can have a two-dimensional representation like you're looking at right now. You're looking at a two-dimensional representation of me and a picture of St. John's area with an iceberg and a piece of paper and a piece from a book, right? And that's all nice and two-dimensional. Thanks to, although there might be a three-dimensional component, I suppose, if you're looking on one of those fancy curved monitors like I've got, right? One of them's curved. This is physics. Although I guess even if it's curved, it's not really three-dimensional, is it? Physics 1104, and this is going to be page 410. I'm going to go over just a scattered few questions from this page. I think we've got 4 questions to go over here. So number 4 is one that I wanted to start off with, partly because, Troy, this is one I believe you left out of your notes, but also because number 4 is actually a really, really useful one to know, right? Although, again, it is important to realize that for any sort of question like this, especially a conceptual one, like this one in number 4, what's correct and what's not correct kind of depends more on what your current course is looking for, more so than what the reality of the situation is. But let me explain. So properties of a graph such as slope and area usually have some significance. Indeed, they do. And no usually about it. They always have some significance. But the question is just, are we recognizing that significance or not? Right? Copy table 2 and state what the slope or area represents, if anything, for the property indicated. If there is no significance, write none. There's never no significance. Come on now. No significance. For shame. No significance that we have learned yet, they could say. But there isn't. There's never going to be no significance. Anyway. Who's got 2 thumbs and is overly technical about questions? This guy. Okay, so we've got type of graph, and we've got slope, and we have got area. Boy. Slope and area. Okay, so distance. I didn't really make my chart big enough, did I? And then velocity. I refuse to call it speed time, because if, like I said yesterday, right, a speed time graph does not have a directional component. A velocity time graph does. So again, this is an example of something that your book is doing, a bit of complication that they're trying to avoid telling you about. But I think, honestly, it's a disservice to not tell you about this, because they could just call it velocity time and just have told you here, oh, velocity is the same thing as speed. Then maybe later on said, hey, wait a minute, velocity actually has a directional component. The thing is, the area under a speed time graph does not translate into the area that the object moves. And why is that? Well, it's because if the object turns and goes backwards, say at the same speed, or like bounces off a wall and goes backwards, the distance that it moved is now decreasing, not increasing, right? But the speed of the object, since the speed doesn't have a direction, the speed would be the same, right? So on a speed time graph, if something, you know, if a ball hit a wall and then came back from the wall at the exact same speed that it hit the wall at, a speed time graph wouldn't even recognize that because it's still moving. It would maybe drop to 0 for a brief second. Maybe the speed time graph would like go up and then down to 0 briefly and then back up again, right? To show depending on how precise they're being. but the resulting speed afterward would be the exact same. But whereas if that happened in a velocity time, right? Say if something was traveling, right? So okay, let me show you this in two different colors so we can do it over the same one. So the black line will be velocity and the red line will be speed, right? So just to show you what I mean. So right here, it's going to hits a wall and bounces. Say, right? So the speed up to this point is going to be the same as the velocity, right? But then when it hits the wall, the speed, say, will very, very briefly decrease to 0. But then the speed is going to, well, okay. So this was the speed was increasing. And then say it bounces back up. Because say the speed decreases to 0 for a quick second, bounces back up, and then reduces back down, right? So that's what the speed would be. Say if it hit a wall and then it went off at the same speed and then started slowing back down to 0 eventually, right? So this would be the speed. So what you would have is if you took the area under this graph, you would have an area under here and an area under here. You would add the two of them together, right? But we know from the situation, like if the ball is hitting the wall coming back, it's actually coming back to the same place. So overall, your area should be 0, right? But here you wouldn't get 0. You would get actually double the area you should. If it was actually a velocity time graph, the velocity would decrease to 0, but then the velocity would, whoa, didn't mean to slip off the edge of my straight edge there. Then the velocity would decrease to negative, right? So say in the speed, you would have an area, say if this was an area of like 9 or whatever, right? It ends up being an area of 9 meters, and this would be 9 meters. And right? So according to S over T, the distance will be 18 m, but this is going to be a negative 9 over here, right? So, and this is going to be 9 as well. But according to V over T, the displacement would be 0 m. Okay, so I guess yes, this is really what I should be mentioning here. So I will, you know what? Now that I think of this, it isn't technically wrong for the book to be saying this. It's just they have to be consistent with the terms that they are using. So let me do speed as well. Right? This is actually a really good lesson now that I'm getting into it. I think this is a really good lesson on some terms that you're going to see later on. Right? Because this is now highlighting the difference between velocity and speed. Speed is just going to show the total distance that something travels. So if something goes 9 meters, hits a wall, comes back, right? The distance it travels is 18. But the displacement, the amount of distance it's traveled overall, is 0, right? So distance has no direction. It's how far something travels in total. Displacement has a direction. It's how far something is from where it started. All right? So, yeah. So the slope of velocity time and speed time, excuse me, in both these cases, the slope is the accel. Right? Because the slope, if it's increasing here, it's how fast it's accelerating. Now the thing is, the slope of speed time graph is not really acceleration, because acceleration does indeed have a directional component. right? Which is one reason why I am drawing an asterisk here, just to point out, you know, right? The slope of st is acceleration in a sense, but with you know, um, well, you know what? No, actually, I don't think it's pertinent to get into that right now. I don't think that's pertinent to get into. So maybe I'll just leave that part out. I know I seem like I'm scattered all over the place here now, but I'm trying to do justice to the different topics that we're talking about here, right? But we do in this course talk about negative acceleration, right, or deceleration, right? So it's when it's going to be slowing down, right? Whereas the area under velocity time, like we just said here, is displacement. The area under speed time graph is going to be distance. Okay? This might be a bit more confusing than what I meant to get into for this unit, but yeah, trying to balance the stuff that you're going to see in your very next course versus the stuff that you're seeing in this course, right? Now, the slope of a distance time graph, we know that one. The slope of a distance time graph is going to be your speed, right? We have talked about that one, the slope of the distance time graph. So if, say, we had distance, actually, I will use a different color again here. Right? So obviously the speed then is going to be the slope because it's the rate of change, right? So and a really important thing to know on any graph like this is that slope of any graph is the rate of change of any I should say any x over t graph is the rate of change of x, right? So when it's a something time graph, a distance time graph, a velocity time graph, a speed time graph, the slope is always the rate of change of that quantity, right? So the rate of change of distance, we can think about that conceptually, the rate of change of distance is the speed. But it's also if you want to find the unit, it makes a lot of sense to think of it like this, right? It's the y unit divided by the x unit. So here the distance divided by time. Well, what's that unit going to be? That's going to be meters per second, right? And what's meters per second a measure of? Well, we know meters per second is speed, right? So speed here is in meters per second, although velocity is also in meters per second, right? That's why I'm sort of conflating the two. But what's meters per second divided by speed? Well, it's acceleration, right? Because meters per second divided by seconds, sorry. Not divided by speed. Meters per second is speed. Meters per second divided by second is meters per second squared, or its acceleration. Now, the area underneath, right? So this one up here. This one up here is the weird one over here. This one's called absolute. And this is sort of what I was fumbling about when we first started talking about this one. This one is actually not covered in your course. So in your course, they want you to write in none under here, so you don't need to really know what this one represents. But the area under a graph, like we say over here, is the integral, or it's kind of like, you can think of it kind of like levels. I like to think of it like that, right? So distance time graph, if we take a derivative, it's like we're going down one level. It's like Inception, right? It's like we're going deeper. If we take the derivative of a distance-time graph, that's taking the slope of it, which tells us the speed. So if we're at distance time, when we go in one level deeper, further into, into Leonardo DiCaprio's dreams or whatever, right? Like if we're going further in, then we find the speed, right? Or if we're doing displacement time, then we find the velocity. And then if we go a level deeper into velocity or speed, then we get into the acceleration, right? We go deeper into that, we get the rate of change of acceleration, which I can't recall the exact term for that one off the top of my head. But if we take the integral, it's like we're going back up one level, right? So remember, the derivative, or the slope, of distance time is the speed. Then the integral of the speed gets back up here, gets back to the distance, right? But is distance time the top level? Well, no, not really. There is no such thing as the top level, really, in physics, because we can keep taking integrals, or we can keep taking derivatives to go down levels or up levels if we want to. And that's going to give us different values. Now, these values are perhaps less useful in a lot of senses. But absolute, what that is it's sort of the measure of how long you spend away from your starting position. Well, that's if it's displacement. If it's distance time, the absolute is how long you've spent at moving at a distance away, sort of. It's an odd value. It sometimes might come up in like calculating roaming charges, for example, on say cell phones, right? Like if a roaming charge increases for how far away you are, what's relevant is the amount of time you spend at what distance, and that is what the absolute is. Right? Now, for your course, you don't need to know this guy. So really, if I was to, how's about instead, if I was to just do out the exact ones that you need to know for your course without all this extra, nonsense that I'm rambling on about here. Right? One reason this one is particularly rambly as an answer is just because this is the kind of topic that always has more stuff you can say about it depending on where you're deciding to stop for your current course, right? And my own philosophy is sort of to carry on and explain sort of the basics, the difference behind it. So distance over time and speed over time. These are the ones you need to know. The slope of distance time is speed. The slope of speed time is accel. The area we'll say is none because we didn't learn that one, right? And then the area under speed time is distance. So if you're asked on a test or something, this is what you're going to give. The rest of what I'm saying here is just to sort of explain a bit of the difference between velocity and speed, and then to explain a bit of the difference between displacement and distance. But anyway, this would be the answer for what this course is expecting you to give. I want to talk about question number 8. So a car is struck from behind by a large truck. The impact lasts 0.1 second and causes an acceleration of 45 meters per second squared on the car. What is the car's change in speed? Right? So, right. If we want to get, well, we know that we're looking to get a value of meters per second, right? So velocity is going to equal the acceleration times the time, right? And this sort of makes sense when we think about it. Or the change in velocity is equal to the acceleration times the change in time, we could say. Yeah, we could say delta v is equal to a delta t, right? But that's kind of obviously what we mean here, right? Because if you're accelerating, it's always in meters per second squared, right? Every second you're accelerating, you're changing your speed by some amount. So if you want to find out how much the speed changes in total, you're just going to take the acceleration and multiply it by the amount of time it spends. So here, since we need to find the delta V, all we need to do is take our acceleration, which is 45 meters per second squared, multiply that by 0.1 seconds. We're going to notice once we do the multiplication, right, that this squared cancels with this second, and we're just going to be left with a delta V of 4.5 meters per second. Right? So the car is struck from behind, and then it reduces its speed by 4.5, because of acceleration, sorry, it increases its speed by 4.5 meters per second. All right, so that's all we have to do for a question like that one, is just to take our formula, right, and then to multiply it out like that. I wanted to do questions, let's see, 10 and 13. While pulling a barge, a tugboat accelerates at 10 meters per second squared to produce a 5 meter per second change in the speed of the barge. How long does that take? Well, that's going to be the same formula, right? Our delta V is equal to acceleration times a change in time. Or we could just say, not really change in time, I could just say delta V is equal to A times T. Would make a bit more sense, right? Because the time is always changing. The times they are changing, right? Tugboat accelerates, so we know the acceleration is, so we're trying to find the time. Yes, okay. So if I want to rearrange this, right, I could say that the change in the velocity divided by the acceleration equals the time, because I'm just moving this acceleration over. So then the delta V is 5.0 meters per second. Actually, I guess for this last one, right, this, oh no, never mind. This was, hold on, 0.10 seconds. Yes. I should have listed that in there like that, because that 10, of course, as we talked about before, just to go back. Actually, let me write that out more clearly so that it's clearer when I send you the notes. The 10 is important there because, of course, that's 2 sig figs, and 2 sig figs there. 5.0 meters per second divided by an acceleration of 0.10 meters per second squared equals time. And we are going to then end up with a unit of seconds, right? Because dividing by a fraction, of course, is the same as multiplying by its reciprocal. So we're kind of multiplying this by seconds squared per meter, right? Dividing by 0.1 is the same as multiplying by 10. So we're going to end up with 50 seconds equals time. Now, we shouldn't actually write it as 50 seconds to be very extremely technical, right? Because just like what I was talking about over here with just now, that tangent, or, you know, flipping back to it, talk about the sig figs. Here now, this number needs to have 2 sig figs, but of course we can't, in decimal notation, we can't represent 50 to have 2 significant figures. Because if we did 50.0, that's not going to work. Sometimes you'll see people do 50 and then put a decimal here and not put a number after the decimal. That's a little bit cheeky, though. We don't actually do that here, right? What we would have to do is 5.0 times 10 to the 1 seconds, right? This is scientific notation, of course, and this is, I mean, it's considerably longer to write this out than to just write out 50, but this is the technically correct way of showing that this number actually has 2 sig figs. Like I said, sometimes you'll see people just put the decimal in and not put a 0 after the decimal, but it's not really how we do it. Okay, and then let's see, question 13. Question 13. I gotta switch to the next page for that one. Donovan Bailey's 1996 Olympic gold medal run, figure 1, we got it right down below here. His winning time for the 100 meters was 9.84 seconds. First part of the race's average acceleration was, excuse me, you need to, 1.86 meters per second squared until he reaches maximum speed, 6.5 seconds, which he maintained until the end of the race. Calculate Bailey's maximum speed at 6.5 seconds. Okie dokie. That's an easier question than maybe it looks like at first, right? Because we're just using the same old jazz. His maximum speed, well, his delta V, or just his V, right? Because he started at 0. So the delta V, I mean, I'll keep calling it delta V just to be precise, but you know, It just means the change in, right? And he was changing from 0, so it'll be his total speed. But it tells us back up here in the question, which I can't really get all in there at once. His winning time, 9.84 seconds, but his first part of the race, his average acceleration, was about 1.86 meters per second squared. So it's 1.86 meters per second squared for the acceleration. And then the time, so he accelerated for 6.5 seconds, right? So then the seconds are going to cancel with seconds. We're going to be left with the unit of meters per second, which we're hoping for. So the delta v, or just the velocity that he reaches, is going to be 1.86 times 6.5. And of course, does now need to have two significant figures, because 6.5 has two significant figures. So that's going to be 12 meters per second. It's going to be the maximum speed that he reaches there. I got to say, Donovan Bailey's 1996, this Olympic gold medal run, boy, oh boy. There are very few examples that I think you see more times in high school textbooks circa like early 2000s, which is when this book was printed, than that race. Let me tell you. People love, although I guess now it must be like every single question must have to do with curling, now that we got that Brad Gujou gold medal as well. I got to say, Canadian gold medal wins we need them. We need them every so often in order so that math textbooks can be updated with new examples. What was his average speed for the whole race? Okay, so that's not hard. His average speed for the whole race, well, speed is just equal to distance over time. I mean, it should be v equals d over t, because d is usually not used as distance. D means displacement. But anyway, like I said, you'll get into that. You'll get into that in your very next course and not in this one. But either way, the average speed is just going to be, well, he ran 100 meters, right? Divided by 9.84 seconds. And this quantity here, right? I'm going to treat this quantity as if it's not measured. Now, of course, it is measured in a sense, right? Because whoever made the Olympic track had to measure the 100-meter track. But for our purposes, we can consider this to be an exact quantity because we're not measuring it ourselves, you know, right? And we're not told. I mean, it's definitely got more than one significant figure, right? It's supposed to be a very exact 100 meters. So I think we can stick with 3 sig figs for this. It is technically a measured quantity, but it's not measured by us. So I'm just going to go ahead and assume that the people that made the Olympic Stadium were able to measure a pretty accurate 100 meters. Because otherwise we'd have to make this into 1 sig fig, right? But I'm going to assume that I can keep it at 2 sig figs because of this 9.84. So I'm going to call this 10.2 meters per second was his average speed. That's all we got to do for that guy. And then for C, sketch a graph to clearly illustrate Bailey's motion. Yeah, I don't know. How about I don't do that? Well, sure. I'll go ahead and try with the graph. It's not that difficult, right? I'm just going to do this freehand. Right now, ideally, you know, for full marks on a test or something, you would ideally be using graph paper. I understand that people don't always have graph paper accessible, but just roughly showing that you understand what's going on here is the main point, right? Because they're sketch a graph to clearly illustrate his motion. Well, I'm going to pick a speed time graph. You could have picked a distance time graph if you wanted to, right? Which would look a bit different because a distance time graph you would need a curve. Actually, how's about I do both those? How's about I do both? So the speed is going to increase sort of linearly like this because we're not told until, you know, it goes along like this. It stays constant. And then I guess, you know, he finishes the race and we just point it down pretty quickly as he cools down at the end. But whatever, right? But the fact of the matter is we're told that he speeds up until about 6.5 seconds. So this is going to be 6.5 seconds. And Troy, because you mentioned that you don't have graph paper and stuff like that, I'm okay with you kind of doing out the graph sort of just like what I'm doing here, where you, instead of labeling every single number on there, just pick the ones that are important for the situation that you're sort of roughly trying to model. And here for the speed time, what we want to show is that his acceleration is roughly constant, at least as far as we're told. The acceleration is roughly constant until about 6.5 seconds, and then his speed is constant for the rest of it. Right? So that should be a sloped line and then a horizontal line. And then, I mean, you know, if you want to be very pedantic like I'm doing here, this will be our 9.84 seconds over here. And then after that, I guess he slows down pretty quickly, you'd imagine. If instead you were doing a distance time graph, right? So a distance time graph, you're going to have, it's going to be accelerating up until 6.5. So we're going to need, say, a curve to be increasing like this, right? So there's going to need to be a slope that increases. And then from there, the slope is going to need to stay the same, right? I've sort of drawn myself into a bit of a corner here because I've made it a bit too steep. But then after this, we're going to have a constant rate of change of distance, or a constant speed, up until the end, at which point it just plateaus because he's no longer, or you could say perhaps that it slows down very rapidly, right, like that, and then plateaus. Yeah, so let's say it's something like that. Now, this last part here at the end, this curve, I'm not super concerned about, right? Like, we're not even all that concerned about what his speed was like after he stopped. Right, that's not part of his Olympic medal, how fast you slow down after you win your medal, right? But if you're doing a distance time graph, you would have to show a curve here for the first part, and then after 6.5, it should become a straight line, and then at roughly 9.84, it should plateau off and become a horizontal line. I hope some of this is making sense. Yes, and I did want to mention on your test there was 2 questions. Well, I never show test questions on stream. Of course I wouldn't, right? Because then students could crib up on them. Oh my God. So there's 2 questions here that I would like to go over, and then I'll move on to my next topic for the day. Let's see. Question 16 I want to discuss. So a long straight line on a distance time graph indicates what? A long straight line on a distance time graph indicates, well, how's about let's do out a distance time graph, or a rough distance time graph. Now, in multiple choice questions like this, there should be something written on the top in the instructions where it's kind of like I've heard like that LSAT, I think, or various other like law tests are like this, where all the answers are right, sort of, but some answers are more right than others. And you're tasked with picking the most correct line, right? So in a distance time graph, a straight line indicates what? That the object is changing speed, object is stopped. Well, what could some straight lines on a distance time graph look like, right? We could have a straight line like this, right? So this black one here, this is a straight line. And what does this indicate? Well, this indicates the object is stopped. It does. It does indeed, right? How about this line, though? That one's straight. That one's straight as well, right? So this is kind of one reason why I dislike distance time graphs, because in a distance time graph, there isn't really there's no real way to represent a negative, right? Because a negative is displacement. Because if I was going to draw a line going down and say that was an object moving backwards, but the thing is, in a distance time graph, it doesn't matter. It doesn't matter whether you're moving backwards or forwards, because distance is always a positive quantity, right? Like if I pace the room back and forth 30 times, and the room is 5 feet long, say if I'm pacing 5 feet long 30 times, my distance is 5 times 6, which is 30, right? But my displacement, if I end up back where I started, is 0. Because I had positive displacement, then negative displacement, then positive, then negative, then positive, then negative, and I end up back in the same spot. But distance, there's no such thing as a negative distance. So, but anyway, this one is the object moving at a constant speed. This one here is so it's moving at object constant speed. And if the object is stopped, we can think about that as constant speed as well. It's a constant speed of 0. Right? So the object is stopped, answer B, that could be correct for one specific type of straight line, which is a horizontal line, right? But then other straight lines, like diagonal ones, those ones are going to mean that the object is moving at a uniform speed. And it does say a long straight line, so maintain a uniform speed for a long period of time. So the answer that they're looking for is going to be C. Right? Anyway, it might be confusing how I'm talking about how like there can't really be a negative line on a distance time graph without going back in time, sort of. Right? You know, but anyway, you will see that in the next course. For now, you can just sort of ignore that notion. But this is partly what I'm saying. How like trying to look at a stripped down version of physics. Like, I mean, even my knowledge is obviously stripped down compared to the total substance of physics in the world, obviously. Like, even, everybody, nobody understands all of it because science doesn't understand all of it. But anyway, my point is, when you try to teach like a really simplified version of stuff, you end up with things that don't make a lot of sense, right? Like, why in the world can't we have negative on this graph? Why couldn't we have a line coming down that way? Well, it's because there's no such thing as negative distance. There is negative displacement, though. Anyway, the next one I'm going to go on to is number 30. Oh, got to scroll down a long ways. They inserted, I don't know why they insert these. Inserting these blank pages is hilarious, right? Like, it's like they want us to print it two-sided, but then when you print it two-sided, it comes out one-sided anyway. Like, why do that? Why not just, if you want someone to print it one-sided, why not just not leave those blank pages there and just have you click the one-sided button? Someone really wanted to waste some paper, basically. It's like, those people that are trying to print two-sided, they're going to print one-sided. And the people that are already on my side and printing one-sided, they can just throw away half the paper. Let's get it. Let's burn some trees down. Anyway, it's silly to me. Question 30. Solve for A using the given equation. V equals 1 over 3 AH. Now, I understand that having it written like so on a piece of paper is a bit annoying. And the person who made this test didn't like write up the math working with Wolfram Alpha or something like that. That would actually allow you to write math workings properly on a computer. They just went ahead and stuck it in there in Word as best they could. But volume is equal to a third AH, area times the height, right? Which is the volume formula for a cone. Volume is equal to a third times the area of the base times the height of the cone. Well, it should be 1 over 3 CH, I believe. Anyway, we're not talking about that. All we're doing is just rearranging this formula. So solve for A. Well, all we got to do then is do the opposite of each of these steps, right? If we want to get rid of a third, remember now, there's a few different ways we can do that. Or we could also call this, V equals AH over 3, if that makes more sense to you. Either one of these are both exactly the same. A third multiplied by AH or AH divided by 3 is literally the same thing. It might make more sense in this form, because we know that if we're dividing by 3, to get rid of divide by 3, we have to multiply by 3. Right? So if we multiply both sides by 3, those cancel. Now we've got 3v equals a times h. And the way to get rid of a multiply is, of course, to divide, right? So we're going to end up with 3v over h equals a. And the same thing over here, right? We can multiply both sides by 3 over 1, and so on, right? But it's always going to work out to be this 3v over h. Okay, but this is an algebra question. This is really not a physics question per se, right? But I guess they just stuck that on the test to make sure to check your algebra skills from your math courses. Anyway, I hope that made at least a small amount of sense. Skip back over here now to my intro screen. Stream is not starting soon, it's already going. So I'm going to talk a little bit about graphing quadratics here now. So that'll only be 2 questions here, really. That is for Betty Ann's current course. So let me go back over, here we go, document display. Change my background again. I'll change my background maybe every time we do this. Let's get the snow pond for this one. There we go. Nice. All right. So this is from the Unit 3 assignment. Betty Ann, I know you've gone on past this already. I just wanted to show a little bit about this one here now, just because I had this sort of queued up from yesterday to get to. This is Math 2101B, Assignment 3. Question 1. Right, so determine the following information from the graph. Well, the main one that I wanted to talk, main 2 I wanted to talk about here today are the axis of symmetry and the vertex. But the axis of symmetry, all the axis is just the vertical line that cuts this directly in half. So honestly, getting the vertex is really just strictly harder than getting the axis of symmetry. Because the vertex, you need 2 coordinates. The axis of symmetry, you just need 1. Right? All the axis of symmetry is just the x-coord of the vertex. Right? Because the axis of symmetry is this straight line here, this one here, that goes up and down straight through the middle. Right? So that's going to be x equals -1. We can see that right there because we can see that the vertex of the parabola is right here. The vertex, as we can see, is -1, -2. I do believe you got everything else correct on this guy. Right? So the min value here, right? The min y value is -2. Right? The x-intercepts, as we can read off the graph here, the x-intercepts are going to be this value here and this value here. So it's going to be -3 and +1. Right? The y-intercept is going to be this one down here, which is about -1/2. -1.5, sorry. Domain, right? X is all real numbers. Range, y is greater than or equal to, it's at -2. Y is all real numbers. That's it. That's all you got to do for those. And you did do that almost entirely correctly. I just wanted to point out here that the axis of symmetry is just the x-coordinate of the vertex because it's just the vertical line that cuts through the vertex. All right, so graph the function that and determine the following information and sketch the graph. Excuse me. Okay. You know what? No, I don't think I actually. You did this one correctly. I don't really think I need to go down through these much more. All I really wanted to point out today actually was that the axis is just the x-coordinate of the vertex. Like that was literally the only thing that I had to mention. You've got like 98% in this unit or something like that, right? So yeah, I think in essence, in effort of keeping the time shorter, I think I'm just going to send you this little bit and say that the Okay. The axis of symmetry is a vertical line that cuts through the vertex of the parabola, and it's the middle of the parabola. All right? I think that's all I really needed to go over for that. Probability and NCR, NPR recap. Okay, Calais, this will be a relatively quick one as well. All right, well, I've got a few questions to go over here. So let me go over, this is 3101A. Oh, let me scroll. Oh, that's the wrong file I've got open. Hold on just 1 second there, Twitch. Hold on 1 quick second. Got to go grab the correct file. I actually have the answer key. I don't like to answer these questions from the answer key. I would prefer to answer them from the version without the answers so that we can sort of talk about it partway through. Okay. Switching on back over. So I'm going to start on question 4. Yvonne tosses 3 coins. She is calculating the probability that at least 1 coin will land as heads. What is the probability as a percent that at least 1 coin lands as heads? Well, we could figure out the probability that at least 1 coin lands as heads because we can get 1, we can get 2, and we can get 3. Or the easiest way to do it is to say, well, what's the opposite of at least 1? The opposite of at least 1 is 0, right? So if we figure out the probability that 0 coins land as heads, or all of them land as tails, then we're good to go, right? So we could go ahead and just list out every single entry in the sample space. That's not hard. It's not hard for this sort of question, right? Because we could go ahead and say there's 3 heads. There's heads, heads, tails, heads, tails, heads, tails, heads, 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 tails, 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 heads, tails, 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 heads, or tails, tails, tails. Those are now, I've just written out every single possibility, right? There's only 8. Well, we know there's 8 because it's 2 potential options for the first one, right? 2 potential options for the second one, and 2 potential options for the third one. That's 8 total possibilities. We could have gotten to that one, right? We could have. And we could have easily said that to get 3 tails, well, t is going to be 1 over 2 times 1 over 2 times 1 over 2 equals 1 over 8, right? And then 8 over 8 or the whole, subtract 1 over 8 is going to equal 7 over 8, or 87.5%. So there's loads of different ways that you could do this one. You could write out all of these ones and then see, oh, 7 of them have at least 1 head. And then say, well, 7 over 8, what's 7 over 8? 7 over 8 is going to be 87.5%. You could count them up like that. Or you could go ahead and do what I did over here, which is often the shorter way to do it, especially when you've got a more complicated situation. Either way, we know that the answer here is going to be option D. Okay, I wanted to talk next about question 8. Scroll down. Jade is about to draw a card from a standard deck of playing cards. Determine the probability that she will draw a black card or a 3. Remember, the probability of something or something else is the probability of one of them plus the probability of the other one, subtract the probability of both of them. Right? Now, again, you might, if you're not super familiar with decks of cards, you will see it right up here, right? On your activity. Here we go. Standard deck of playing cards. There it is. It's right there for you, which is, because really we're not testing you on if you know what goes into a deck of playing cards. We're testing you on, if you can figure out the probabilities. So how many of these cards are black? Well, we see it's half of them, right? But I'm not going to write it out as half right now. I'm going to keep it with the same base so that my addition is easier. So that is, of course, going to be 26 out of 52 black cards. Probability of 3, well, out of 52, how many cards are 3s? Well, we can see up here that there's these guys, right? 4 of them. So it's 4 out of 52 are 3s. And then how many of them are black and 3? Well, there's this one, 3 of spades, and there's this one, the 3 of clubs. So it's going to be minus 2 out of 52. So that's going to equal 28 out of 52, which in simplest form, we can divide the top and the bottom by 4, and we end up with 7 out of 13, right? And if we scroll back down, to question 8 here. It's option C. There we go. All right, question 9. I mentioned question 9 as well. Question 9 is a good example. Rick has 6 loonies, 4 toonies, and 2 quarters in his pocket. Boy, he's got a lot of money and change. He needs 2 loonies for a parking meter. Reaches into his pocket and pulls out 2 coins at random. Which expression best represents the probability that both coins are loonies? Okay. So for question 9, well, what's the probability that his first coin is going to be loonies? Well, we know that a probability, right? So prob is always fav over tot, right? Favorable over total, like so. So, what's the total number of coins that he's got? The total number of coins that he has, 6 plus 4 plus 2 is going to be 12. Right? And the number of loonies is going to be 6. So it's going to be 6 out of 12 on the first pull, right? Which is the same as 1 out of 2. Probability of the first loony is going to be 6 out of 12 or 1 out of 2. Probability of loony 2 given loony 1, right? I'll write it out totally pedantically accurately here, because that's what we're doing. Probability of loony 2 given that loony 1 has already been taken is going to be 5 out of 11. Right? So, the probability of loony 1 and loony 2 given loony 1 is going to equal these two multiplied together, which is going to be 1 over 2 multiplied by 5 over 11, which is, as we see over on the side, that's option D. There we go. Want to do numbers 13 and 16? And I'm going to go ahead, yes, we should have enough time, should have plenty of time, and I'll go ahead and write up a few examples for Bev. So in a state lottery, if you purchase a ticket, you choose 6 different numbers from 1 to 40. Oh, hey Slayer Darth, hey, how's it going? If these 6 numbers match the 6 numbers drawn by the Lottery Commission, you win or share the top prize. Okay, Calais, you were very close on this one, and this one's kind of a sneaky one again. Right? Because us teachers we're always sneaky. Right? Here, to someone who doesn't play the lottery, it might seem like, yeah, it would need to be P, right? Because the order does matter. But guess what? But it actually doesn't. The 6 numbers can be in any order here, because in this state lottery, it doesn't say that the numbers have to be in order. So we're actually just going to go ahead and use C, right? We use 1 over 40C6. Slayer Darth, how's your readings going? If you're still furloughed, I guess. I don't know how stuff is opening up across the pond over there for you. We're not quite opened up yet over here, and we still don't know if we're going to be open for September or not, but we'll see. We'll see how that goes down over the summer. Question 16. Yes, 16 was the last one I wanted to get to for Calais' course, and then building a new community website for STEM educators on Twitch. Oh, interesting. Yeah, that's pretty cool. This is math 3101A. Yeah, if I'm I don't know what in the world my teaching is going to look like in the fall, right? But yeah, I don't know if you've been around when I've said this, but I am this stream is ending as of Friday, right? Because then I'm off for the summer. I'm unemployed for the summer, so I'm off on my own recourses to fill my time with something or another. Sometimes I work at to do some tourism work in the summer, but that's not going to happen this year, not with COVID-19. So there ain't going to be any tour guiding or anything for me. Not this year. Or sometimes I volunteer up at a museum. I'm not going to be doing that either. Right? But yeah, I may. Yeah, feels bad, man. Feels bad. Yeah, I may be back in the fall though for season 2. It depends on if my program is still online or if we're on site. But if I'm back in the fall, yeah, community for STEM educators would be a very interesting thing for sure. So a fair coin is tossed 3 times. The tree diagram below represents the possible outcomes. What are the odds in favor of tossing 2 heads and 1 tail? Right? Renewed for season 2, lol. Yeah, basically, right? I'll have to get some more graphics maybe and get the sort of scene transition, right? With the NL Mathman symbol to zoom in and out. That'd be fun. Um, yes, right. So the probability, of course, we know is favorable over total, but we know that our odds, or odds in favor, are favorable to unfavorable, right? So, what are the odds in favor of tossing 2 heads and 1 tail? Well, realistically, what should be done here along the side, and what you could have written in over here, is to write out all the full sample space, right? So I'm just going to do that over here now, right? But that tree diagram that they give you in this question, it isn't really quite finished, right? Because they should have a sample space, which over on the side there summarizes the different paths along that tree diagram. So I'm writing them down in the order that they would be. I didn't print this page off. I guess I kind of should have. So I printed it off. I could be writing it in just alongside like I'm encouraging you to do. All right, so those are your 8 results. So what are the odds in favor of tossing 2 heads and 1 tail? Well, which of these fills that situation, right? Well, there's 2 heads and 1 tail. There's 2 heads and 1 tail. There's 2 heads and 1 tail. Looks like that's it. Yep, that is indeed it. So we know our favorable is 3. Unfavorable is the rest of them, 5. Therefore, the odds in favor are going to be 3 to 5. Here we go. That's it. That's all I got to do. Okay, so Calais, that was what I wanted to get to off of your activity. I believe you are intending to do your exam tomorrow, hopefully, provided your schedule works out. So hope that's that's the wrong window. I wanted my intro window. I didn't want to go looking at myself there on the screen, bouncing around all willy-nilly. Okay. So now I'm going to do a little bit on sine and cosine laws. Now, I know Bev is not going to be watching because I don't think she's able to watch, at least not live for sure. But hopefully she'll be able to watch the video recorded, and if not, just read the notes is fine. But I'm gonna at least keep streaming it so you can, so it'll be there if you need it. So let me switch over to the Math 3102C activity. I'm gonna do questions 1, 3, and 4. And use this scene. Don't use this scene as much anymore. Okay, so we're going to determine the missing side lengths of each of these triangles over here. Oh, no, I got to zoom out one more. Okay. 3102C. Assignment 2. So let's do question 1. Yeah, I'll go down through all of these ones here. Question 1A. Determine the missing side length to the nearest, it says nearest tenth of a meter. Right, so the triangle that we are given Doesn't really matter. Mine's not going to end up looking very similar to the one in the diagram there, but that's not super important. It's a triangle. 101 degrees here, 45 degrees here, 36 meters here, x there. So that's the one that we're going to try to find out. Now we know we have two different formulas that we can use, right? A sine law and a cosine law. And sine law is useful when we have a pair, a known pair of side and angle opposite it. And we also know one of two of another pair, right? Which we will always know, because if we know, well, I guess not necessarily. Yes, we will. Because if we know one other angle, we know all three angles, and if we know one other side, then we have enough to keep going. Anyway, if we have a pair, we can go ahead and do this, which is A over sine A is equal to B over sine B. Now, Bev, later on in some of your other questions, I cautioned you about skipping ahead and using an already solved version of the equation, right? I would much prefer for you to start off with an equation like so, and then carry on through the rest of it, right? A over sine A. So here, we're going to use this one, right? So we're going to have 36 over sine 101, right? And that's going to equal our side x, which we don't know, over sine of 45. So what we're going to do is we're going to multiply both sides by sine 45, kind of, because over here, right, we're dividing by sine 45. So to get rid of that, we're going to multiply. So we're going to have 36 times sine 45 divided by sine 101 equals x. Now we just take that and fill it into our calculator. 36 sine 45 is that, divided by sine 101 equals this. 25.9. Your answer was close, Bev. I'm not quite sure why it was off a little bit for 1A. Maybe it was just to do with the rounding that you've chosen. But I did want to show you that this is the working that I'm going to expect for these ones. For B then, now I can definitely zoom in a bit more. For triangle B, then we have, this is 64 degrees, 32 meters and 32 meters, and this is D, an unknown amount. So now as we see, we don't actually have a pair, do we? We don't have a pair of, although we kind of do though. We kind of do. This one's a little bit cheeky. We can use a sort of sneaky workaround here to actually use sine law again. And it's because these two sides are the same length. Because those two sides are the same length, we know that this angle and this angle had to be equal, which means we know that the 116 that's left over is split evenly between those two guys, right? So we can actually go ahead and use sine law here, because if this is two equal angles to make 116, we know that each of those has got to be what 50, 58, right? But never you mind. You don't actually need to do that, because what we're going to do is we're going to go ahead and use cosine law, right? So we know that c squared equals a squared plus b squared minus 2ab cos c. Now again, you were doing this one correctly, but I wanted to show you the way to actually write out the working like we do, right? Which is to represent it all in here together. So we know that this angle that we're looking for, which I'm going to write down as d squared now, that's going to equal 32 squared plus 32 squared minus 2 times 32 times 32 times, oh my, I'm running out of space, cos 64. Yeah, that's clear enough, I think. Cos 64. So d squared is going to be 32 squared, boy, to the negative 1. That was odd. 32, okay, you know what? 32 squared times that by 2. So that's going to be 2048 there. Subtract 2 times 32 times 32 times cos of 64 minus 897.8. I'll call that because we're rounding to the nearest single decimal point. 2048 minus 897.8. It's going to be 1150.2. And we're going to do d is equal to the root of 1150.2. The root of the answer, d is going to be 33.9 meters. There we go. All right, so that's how we're going to find these ones with, like I said, so this was sine law, this one was cosine law. Just to keep on going down to part C down here. Oh, I've really got to, I got to change my attire. I got to change my, I'm sticking with this sweater for now, just as like my standard like Mr. Rogers get up as like a teacher uniform almost. But my lord, it is 30 degrees outside, and I am here with no air conditioning, and I am about ready to stew in my own juices over here. Like it is, it's a more vivid description than maybe you needed, Twitch chat. Maybe indeed. But you know what? Summer comes to Newfoundland eventually. She might not be here for long, but she shows up for a bit and sort of, you know, it just makes everybody complain about flies and heat for a solid, you know, solid month. And then it's gone again, right? It's one thing about Newfoundlanders. We'll always find something to complain about the weather. And, you know, most of the time it's cold, right? But the worst part, the really cold part is great. Like the actual, like we see behind me here, like look at all the snow pictures I've got in my stream, right? The actual cold snow part is wonderful. It's that in-between part, like November, when it's just like kind of 1 degree and just like pissing rain all the time. And like it's not cold enough for that rain to be snow, but it's, you know, although this past year we did have Snowmageddon, right? We saw a picture of that on Monday. So my goodness. We have had yeah, maybe we've had a year where the weather has really been uncooperative, I suppose. We even had our dry run, right? That was our COVID-19 dry run, shut down for a week, 6 days. Well, there was no seven working days, so well more than a week. But here now we can use sine law, and we have to try to find x over here. But the thing is, we're not going to use our 114, right? Because the 114 is opposite of this angle. So what we have to do is we have to find this angle down here, right? So 180 subtract 114 subtract 38 is going to give us this angle down here. .28 degrees. It's going to be 28 down here. So this is the angle that we have to use for opposite of x, right? So remember our formula. Our formula is a over sine A equals b over sine B, right? So that's going to be 15 over sine 38, which is this one and this one, that's the one we were given, is going to equal x over sine 28. So we have 15 sine 28 over sine 38 equals x, because this part moves up here. Now again, right, I really don't want you to try to jump into this part here, because I noticed one thing that happened in one of your later questions, and one that happens very frequently, this is not a personal thing, this is extremely frequent, that students try to just say, oh, why am I writing out this step and this step? I can just cut straight to this step. I know what I'm doing. But then it's really easy to put the wrong angle in the wrong spot, and then you just don't get the question right. But if you start from this point and follow the rules of algebra, you're going to always get them in the right spot. So 15 times sine of 28 is going to be that, divided by sine of 38. So we're going to have this. 11.4 equals x. Right? And that's the side that they're looking for you to find in this question. 11.4 equals x. I want to do questions 3 and 4. So let's skip down past that. Okay, that's not too bad. Yes, so I got three more parts to do. So this is going to be math 3101. 3102C. Unit 2. New question 3. Zoom in a bit more on our triangle up here. And draw E out. Draw E out like so. It's an angled line there. It's a line there. It's a line there. 27 centimeters. 77 degrees. 52 degrees. Okay? So we're asked to find all the missing sides and angles. All the missing sides and angles. Well, we can find this angle up here, right? This angle up here is relatively easy because we can do 180 minus 77 and minus 52. That's going to equal 103 minus 52, which is 51. Okay, so we got that one. That wasn't hard. Now we're going to go ahead and we can use this pair now to find all the other sides, right? Because now we can say, well, we have our A over sine A equals B over sine B. That's our sine law, right? So 27 over sine 77 equals, I'll call this X and I'll call this Y, equals X over sine 52. So we have 27 sine 52 equal over sine 77 equals X. 27 sine 52 divided by sine 77. 21.8. 21.8 cm is X. Right? And now let's go ahead and, let's get the last one there. Let's get Y. So again, I'm going to use A over sine A equals B over sine B because I do have a pair again, and I'll use the same one to start off. 27 over sine 77 is going to be Y over sine 51. Now, of course, sine 51 and sine 52 are going to be very close, obviously, because the numbers are very close, which means these side lengths are going to be extremely close as well. But I still want you to show yourself doing it out and not just put in, like, you know, something very, it's 21.7 or something like that, right? For sine 77 equals Y. 27 sine 51 divided by sine of 77, 21.5. There we go. cm. Right? So that's now finding everything for 3A. Let's go on down now to 3B. I'll continue that one down a bit more to make it a bit more faithful to how it looks on the sheet. There we go. So what have we got here? We've got 101. We've got 24 meters. We got 39 meters. Right. And these are already labeled. I'll write in the letters this time. E, F, and D. Okay. So now this is the one where we don't have the ability to use sine law or cosine law. Sorry, we can use, obviously, cosine law. We don't have the ability to use sine law because we haven't got a pair, right? So if we want to find one of these other sides, like say I wanted to find this side over here, right? Now I'm going to, so I'll call this is lowercase d. So I know that d squared is going to equal e squared plus f squared minus 2EF cos of capital D. They're like so. Right? So side D squared is going to equal 24 squared plus 39 squared minus 2 times 24 times 39 times cosine of 101. So, Bev, I see the way you were doing these ones. You were doing sort of them bit by bit and then putting them back together in the end. As long like where this is your last course, you know, I understand that you might want to take sort of a shortcut method here, but I do still want you to be able to show doing it with the proper algebra, kind of like what I'm doing here, which is listing it all out and just sort of working through each part of the equation. I know it might seem like just splitting hairs to ask you to do it this way instead of writing it down differently, but it really is important if you were to go on and do other math after you finish here. Right, now we come up with a negative. Right, let's try that again. Did I do that right? 2 times 24 times 39 times cosine 101. Oh my god, it is. It is negative. So what do we do? Well, it's going to be minus a negative 357.2, I'll call that. So that's just going to be a plus. Right? So d squared is going to be 576 plus 1521. 2097. That's going to be a plus then 357.2. So d squared is going to be 2454.2. D is going to be the root. I'm just going to show out every last little bit of this. The root of 2454.2. So the root of that answer, 49.5. All right, so we know that D is now 49.5. Now we have a pair. We have a pair of angle and side, and we can use that pair of angle and side to find one of our other angles. Once we find that one other angle, then of course we can just use the 180 rule to find the last one. So I'm going to do this one over here. I'm going to try to find angle E. Right? So we know that E over sine E, right, is going to equal D over sine D, like so. Right? Angle E is the one I don't know, so I'm going to leave that as a lowercase e. Sorry, no, I do know sine. I basically said that, right? Angle E is the one I don't know, so I'm going to leave that as a capital E down here. And then side D I just found. Side D I found to be 49.5. And we are rounding, so it's not going to be maybe 100% correct. But now we've got to a point here. Now we've got to a point where things look a little bit different than what we're used to, right? And the one reason I wanted to point this one out, Bev, is because here now we're trying to find a sine, the angle in the sine, and not one of the ones on top. Now your book does mention that you can use a different form of the sine law, but it's not a different form. It's just the same form, right? And this is sort of part of the point of what I'm telling you is for the algebra skills. What we can do is we can just flip both sides of these. If you want to get the value you're looking for on top, that's totally fine. That does make it a lot easier to get. So what I'm just going to do is I'm just going to flip both sides. All right, this is just going to make it a touch easier for us. So I'm going to call this sine E over 24 equals sine 101 over 49.5, like so. Right? So now I'm going to multiply across. Sine of E is going to equal 24 sine 101 over 49.5. And that multiplication that I did there to get to 24 over there was exactly the same as what we were doing up here to get this sine 52 up by the 27, right? So now I have sine E is going to equal 24 sine 101 divided by 49.5. Now, here we definitely need to write down more than one decimal point, right? So sine E is going to be 0.4759. So what we're going to do now, I'm sort of running out of space here, but we're going to do the inverse sine. So E equals inverse sine of 0.4759. So E equals, and I'll show you on the calculator here, right? Now, I think you knew how to do these ones pretty well because it did look like you were taking the inverse sine correctly, but it's right here. Second function of sine. On every calculator, it'll be somewhere a little bit different, but it looks like you were finding it correctly for yours. So E is going to be 28.4 degrees because we were told to round to one decimal point for all these answers. So that's 28.4 degrees. Then now this is going to be a red angle over here. I'll do that one. So to find the red one, I'm just going to do our normal, our 180 minus 101 and minus 28.4 is going to equal 50.6. This one is 50.6 degrees. Right? So that's all we're going to have to do to find these ones. Now, like I said, this is a little bit different, but you were solving these same ones correctly in other places on the assignment. So I'm not worried about your ability to sort of solve these or to understand them. I just really want to make it clear that the algebra, when we're doing them, should be done out this way, right? And it does help make sure to remove some of the potential for error, right? Because for the sine law ones, you were trying to jump in at this stage down here, right? And say, well, okay, I know after I reorganize it what it's going to look like, so I'm just going to go ahead and jump in here. But the problem there is, like I said, if you accidentally put the wrong side, like the 49.5 up here and the 24 down below, well, of course you get a totally different answer than what you were supposed to get. So following it through step by step with the various algebra can be a lot more useful. Now, I've got one last question here for you. We're going to do question 4 over here. Okay, so a radio tower supported by 2 wires. Well, that's way too zoomed out to see. Oh my lord. What kind of eyes do I think my viewers have? What kind of eyes do I think I have? I have worse vision than most people. Radio tower supported by 2 wires on opposite sides. One wire makes a 52-degree angle with the ground and is 20 meters in length. The other is 74 with the ground. Determine the distance the wires are apart. Okay, so now I'm going to zoom back in. The reason I didn't switch to a different scene is because I do want to use this one to have this up in the corner here. There we go. This is question 4. Line here, here, and also here. There we go. 20 meters, 74 degrees, 52 degrees. And then what we're trying to find is the distance they are apart, so we're trying to find this guy down here, x. Okay? Now, we know now that we can indeed go ahead and use sine law here, right? Because we do have a pair. We have a pair of 74 and 20. We also can quite clearly find this angle over here, right? Because we can do our 180 rule. 180 minus 74, excuse me, minus 52. That's 106. 106 minus 52, which is going to be 54. So that one's 54 degrees there. So now, armed with that piece of knowledge, we can go ahead and use our sine law. Right? So we're going to have 20 over sine 74 equals x over sine 54. Then we take and we cross multiply to put this one up over here. We have our 20 sine 54 over sine 74 equals x. So 20 sine 54 divided by sine 74, 16.8. That's it. That's the whole question. All right, so that one was just as short as like one part of the other ones that we were doing. And it's worth a lot more, right? Because the only difference is that this one's a word problem where you have to read the question a little bit first. But, you know, they drew a diagram for us, and we just had to know to find the horizontal one, right? And just ignore the fact that it looks like it's two triangles split in the middle, but it's not, of course. It's just one big triangle. But either way, that is going to be, that's it for today, right? Because that was, yes, the graphs, quadratics, probability, and sine and cosine laws recap. Boy, and we're just getting in, just basically on time as normal. A little bit of coffee to some questionable hydration. But thanks for being here with me again for today. I hope that was useful to you, informative. Yeah, we'll be back again tomorrow. Tomorrow will just be business as usual on day 62. And for Friday, day 63, well, I'm not quite sure what the stream will look like for day 63, but I am going to do one. I'll try to clue up whatever we've got left. And like I said, some of my students, maybe about half, are transferring to a different one of our campuses that will be open all summer. So, and granted, it won't be an on-site. Doggos being doggos? Yes, they are. They are indeed. They're about to sniff me over here. I guess they were probably like they found like a mouse or a meadow vole or something like that, right? And they get whenever there's a little like twist or something in the grass or some alluring smell, I guess they get it's very like intense focus on it, right? Flurry will go over and just sort of stick her nose right down in the grass and root around down in there, very very possessed of focus all of a sudden, and then pop over to someplace else very suddenly as well. That's there's loads of videos of dogs doing that kind of stuff, of course. Yes, thanks for being here for today. Like I said, tomorrow's stream will just be business as usual. Then for Friday, well, I'll find out what I'm going to do. What I'm going to do then. Like I said, we won't have our normal farewell barbecue for the summer this year, obviously, right? Maybe I'll have a farewell barbecue of my own and stream that. Probably not. I'm not gonna try to take my my streaming setup outside. Don't really have the setup for that right now. Maybe I'll eat some stuff that I previously barbecued on stream. That'll be a way of acting like we're having a barbecue together. We'll all do some mukbang, right? That's what it's called, mukbang, right? Social eating. Yeah, maybe we'll make it a social eating stream on Friday. Hilarious. I'll change my category for the first time. I didn't even change my category to. Didn't know you had summer in Canada. That's a good point. That's a good point. We don't really. Although today it is like a solid 30 degrees, like Celsius. I mean, like real degrees, outside today, which is like sweltering, right? Just like we're kind of like Scandinavia for that, right? We get summer for about 2 months, and it's quite nice when it's here, but it gets very warm indeed for a while. Although Newfoundland is a maritime climate, of course, because we're stuck out directly in the middle of the Atlantic Ocean. So sometimes our summers are a bit more muted, but these past few years it's been fairly warm. It has so yeah, there's actually a heat warning. Environment Canada issued a heat warning for the past 2 days because it's been up to 30 degrees, over 30 with the humidex, like 35 with the humidex. And like not a lot of people even have air conditioners because some years like the most you'll get is like mid-20s or something, and you don't really need air conditioning then. But then all of a sudden you get like 35 with the humidex and you've got no air conditioning, and boy, oh boy, it can be a real trial for a few days. Remember last year, Canadian Tire, which is Canadian Tire is a hardware store, right? They totally sold out of fans and AC units and all that in the middle of the summer. I don't know if people have learned their lesson. I haven't. It's about 86 Fahrenheit. Yeah, we could go through calculating that. I'll trust you on that one. That sounds about right. Mental arithmetic is sharp. Yeah, excellent. Right? What is it? The plus 32 and then times by 5 over 9? Right? Or 9 over 5? Anyway. I don't have the formula in front of me. But yes, thanks for being here today. I'm going to go now and clue up a few more of my teacherly duties for the day. These are long days this last week getting everything done, but we'll get through it, and then it'll be a nice break for everybody. F equals c times 9.5 plus 32. Yes, 9 over 5, not 9.5, 9 over 5. Yes, thank you. All right, thanks for having my back, Slayer Dart. And I'll hope to see you again. What? We're 9 to 5 because of the car wash song. Oh, I don't know that one. All right, I'll have to. I had to go get some work done there, or more work. I mean, constantly. Anyway, see you again tomorrow.